You know about this. And key for SQ1 is posted. Please examine the key. If thereafter you have questions regarding grading, see your TA. The TA graded it. And only at that point, if you are still not satisfied, do you see me. So we proceed with Chapter 19 stuff. Now getting into the fun part of Chapter 19. You have so far examined semi-soluble salt equilibria, for which the solubility of the salt in question can be calculated straight away from the KSP and the KSP alone for the semi-soluble salt, like silver chloride, silver chromate, and there are some other examples. Why so? Because the component ions of those salts do not exhibit any Bronsted-Lowry acid-base properties of consequence. But most semi-soluble salts do not show that simplistic chemical behavior. Most semi-soluble salts are composed of an anion, which in addition to being a reactive anion, an anion which will react with a number of cations to make precipitates, like carbonate ion. The anion in question also exhibits appreciable Bronsted-Lowry base properties. So now the plot thickens, because now if we wish to calculate a very important property of the salt, like its solubility, in addition to the KSP equilibrium, you have also to pay attention to KB for the anion component of the salt, like calculating the solubility for a saturated solution of teacher's favorite weapon, which is principally calcium carbonate. A brief demonstration which parallels what most of you folks have already done in laboratory. Assignment 3, saturated calcium carbonate solution, where for this system you are asked to observe pH. I'm using the indicator phenolphthalein. I collected some deionized water from our deionized water spout over there. We'll lace the system with a few drops of indicator phenolphthalein. Observe no color, because, as I expect you know, phenolphthalein exhibits a red-pink coloration beginning to set in at a pH of about 9.2. And as the pH rises above 9.2, the red-pink coloration will intensify, because now you're looking at the anion species derived from acid form of phenolphthalein. The color of the acid form of phenolphthalein is now seen by us. It is without color. But the anion form of phenolphthalein is a much lower energy system and is capable of interacting with frequencies of radiation from white light. The result of which is that we see color. So, let's put in some calcium carbonate. This is high quality, reagent grade, very pure stuff. Sometimes this does not want to show us a pink coloration. Appears to be showing that stubborn behavior now, because our deionized water has a habit of trapping an abundance of CO2. What does that do to the pH of the deionized water? It makes the system acidic. So I'm going to run some more water out of the deionized water spout. Let's try this investigation once again. Oh, neat indicator. You still going to be stubborn? Nah, we're starting to get there now. Are you seeing a distinct red-pink color even though it's rather faint? Well, if I run some more deionized water and repeat this, we'll get a deeper pink color. Because I don't know how much water I got to run out of there before I start getting deionized water that's not containing much CO2 dissolved within. But I think that's good enough. Shows us we got a distinct pink color, red-pink color. So, again, given that phenolphthalein doesn't show us discoloration until we get pHs of above 9.2, we know the pH is above 9.2, hardly the pH of deionized water, which if it were pure deionized water would be 7.0. If we investigated this pH, solution pH more carefully, we'd get 10.0. And that's what you folks were asked to do in 46 laboratory. And as I asked last time, many indicated with a show of hands that you've already done this. So this demonstrates the truth of the statement that if we're going to get the solubility for calcium carbonate in deionized water calculated correctly, you have to pay attention to Kb carbonate ion. That means there are two equilibria which are germane to this issue. The dissociation equilibrium for calcium carbonate, for which the K value is what? KSP calcium carbonate. And here's the Kb equilibrium for carbonate ion. So given that, calcium ion itself in water solution shows no appreciable acid properties as a hydrated metal ion. Calcium ion does form a defined hydrate, a hexahydrate, but it's got a K value on the order of 10 to minus 13. Nothing we're going to see with our indicator methods of analysis available for us in 46 laboratory. So practically speaking, when the calcium ion hits the solution, it remains as such. It engages in no further chemistry. That means if I dissolve S moles per liter of this stuff to make saturated calcium carbonate solution, the molarity of calcium ion will be the same as the solubility of this stuff. Call it S for solubility. But the carbonate ion molarity, although it's initially S, because the stoichiometry of this dissociation reaction says, if this puts S moles per liter of calcium ion in the pot, it also puts S moles per liter of carbonate ion in the pot. But carbonate ion doesn't sit there at S moles per liter. It engages in further chemistry by this process. And based on the pH of 10, which arithmetic in the notes show you, you can recognize that the ionization extent of carbonate ion, or call it hydrolysis extent if you prefer, the extent of carbonate ion reacting by this process is on the order of 70%. That's substantial. And you shouldn't be surprised at that. We've done stuff like this before in Chapter 18, have we not? Kb carbonate ion is 2.1 times 10 to the minus 4. That's a lot bigger than 1 times 10 to the minus 7. And the initial molarity of carbonate ion in this solution is large or small? Is calcium carbonate particularly soluble in water? Have you ever cooked eggs by hard boiling such? You know that calcium carbonate's the main ingredient in eggshells? On hard boiling your eggs, have you seen the shell dissolve? Well, if you hard boil your eggs in acetic acid solution, you'll see the shell dissolve. But I don't know that you'd like the egg at that point. Do you know that calcium carbonate is the principal component of crustacean shells? Scallops, oysters? When's the last time you saw an embarrassed scallop? Oh, my shell dissolved. You haven't seen that, have you? You think there's a lot of water in the ocean? Yet, these shells of crustaceans remain intact. How about that? What's that tell you? Calcium carbonate is or is not particularly soluble in water? Is not, you betcha. So then, now given that we have available KSP for calcium carbonate as well as Kb for carbonate ion, you wind up with two equilibria, two simultaneous independent equations composed of two unknowns, S and X. So you can solve this rigorously to calculate the solubility of calcium carbonate. If you do such, which is shown on page 19.7 in the notes, you will get the experimentally measured solubility of calcium carbonate at 25 degrees centigrade. Calcium carbonate in deionized water, 1.4 times 10 to the minus 4 moles per liter. Not particularly soluble, as we had known before we even looked at the result of the calculation. Question 19.8. Saturated silver carbonate solution also shows a pH of 10.0. Based on this data point, what might you tell me about the solubility of silver carbonate compared to the solubility of calcium carbonate? Given that saturated calcium carbonate solution, pH is 10.0. What can you tell me about the comparable solubilities of these two carbonates, silver carbonate, calcium carbonate? They're very similar? You're damn right. Because they're showing you that these data points, these pH data points are showing you that the carbonate molarities at equilibrium in these systems are about the same. As it must be, because the hydroxide ion molarities in these systems are about the same, and the source of hydroxide ion is the hydrolysis of carbonate ion. Saturated silver sulfide in deionized water. pH is 7.0. What fair conclusions can we make about the relative solubilities of these two materials? And what fair conclusion can we make about the absolute solubility of this stuff?
Sulfide is very soluble.
Well, let's try them one at a time. Solubility of silver sulfide versus solubility of silver carbonate. Which material is far more soluble? Silver carbonate. That is correct. Why is that correct? Go ahead.
The pH of the silver carbonate solution is much greater.
That's true. What's that mean?
Sulfide, and the sulfide is a much stronger base.
That's true.
So there must be much less sulfide anion
Put in solution.
in solution.
That's right. That's exactly what this means. Because sulfide ion, on contribution to water solution, will hydrolyze and in so doing convert the hydroxide ion and HS minus to what extent? 100%. Hey, no equilibrium control on the hydrolysis extent of that stuff. So if these two salts, silver carbonate and silver sulfide, had the same solubility, which saturated solution pH would be higher? Silver sulfide, you're damn right. But what are we seeing? We're seeing that the pH of the silver carbonate solution is 1,000 times more basic. The pH shows us that that solution is 1,000 times more basic than the silver sulfide solution. Now then, since the silver sulfide solution, saturated solution pH is 7.0, what can we say absolutely about the overall solubility of silver sulfide? What can we say about its absolute solubility?
It's very small.
Tiny? Moderate? Damn tiny? Ultra minuscule? What would you like to say? Ultra minuscule, because this saturated solution pH is the same as the damn solvent. So how much silver sulfide are we dissolving? Not much at all. Because if the 2 sig figs or 1 sig fig, it's not changing the pH. In fact, the 2 sig figs, the pH of the system will still remain at 7. You have to go to 3 sig figs before you see this solution show a pH that rises above 7. Well, maybe 2 sig figs. I think it was about 7.02, something like that. I don't remember. At this stage of the game, if I ask you to calculate the solubility of silver sulfide in water, what equilibrium would you consider? Well, you'd consider KSP. And do you have to pay attention to something called KB sulfide? To what extent does sulfide hydrolyze? 100%. Forget KB sulfide. It's gone. 100%. Okay? And what else? Yeah, KW. Because this system is damn dilute. How about that? So right now, if I told you to do this calculation, you should be able to handle it. But that's all right. I'll let you dwell on it for a while. In 5 minutes, I'll tell you to handle it. How's that? I will wait a little bit more. Let's pursue with other fundamental considerations germane to chapter 19. On page 19A, we choose to pursue the issue of the solubility of calcium carbonate in a water solution buffered at pH 8.00 with the stipulation that the only chemical effect exerted on the system by the buffer is to preserve pH. In this water system buffered at pH 8.00, before we do any arithmetic, how will the solubility of calcium carbonate compare to the observed solubility in straight deionized water, where the solubility value, as I have here written it for you, is 1.4 times 10 to the minus 4? How will the solubility of pH 8 compare to this 1.4 times 10 to the minus 4 molar value?
Solubility in the buffer is less.
I had a vote that the solubility of calcium carbonate in the buffer is lower than the solubility in straight water. That's one vote. How many supporters do I have for this vote? How many supporters do I have for the statement that the solubility of calcium carbonate at pH 8 will be the same as its solubility at pH 10? Nobody's fallen for that one. Uh-oh, I saw half a pencil over there. All right, that leaves one remaining consideration, which is the solubility of calcium carbonate in a system buffered at pH 8 must be greater than 1.4 times 10 to the minus 4 molar. How many vote for that? I see a few votes like this. That's a third of a vote. Now, I'm going to ask the real rotten question. How many didn't vote? $20 from each of you. Beer and pizza paid for by you. Because you didn't participate, damn it. And we don't accept that behavior on your part, right? You know how I operate. Double beer and pizza fee. $40 a piece. Is this pH 8 system not more acidic than pH 10? Is this system not 100 times more acidic? If you want to kill carbonate ion, which is a base, do you subject it to acid treatment or base treatment? Which system is more acidic? pH 8. Which means in pH 8 we're killing carbonate ion more effectively than we are in deionized water where we get a pH 10, right? What impact does that have on solubility? The more effectively you murder carbonate ion, the greater the solubility, damn right. That's the kind of thinking you want to do before you start doing any arithmetic. Pay attention to the chemistry of the system, always. Does it now sound ever so obvious why we've paid a great attention, detailed attention to chapter 18 before we started this stuff? Because just about everything we do in chapter 19 depends on acid-base chemistry. So if we were to try chapter 19 before chapter 18, we'd be hopelessly lost. Now then, since we've recognized what we're looking for, let's get on with the arithmetic. Knowing that the calculated solubility, if we do it right, it's got to be a number bigger than this. I'll write this as K. Up here I wrote this, the equilibrium reaction for which this is K, right here. Okay? And I asked the question, two questions in fact. Is this equilibrium applicable to S, the solubility for calcium carbonate calculation? Notice that to obtain this equilibrium reaction, all I did was to add this one and this one together algebraically. That's all I did. Well then, is this equilibrium reaction not a reflection of a combination of these two equilibria? The equilibria which are germane to the system? Yes or no? Yes. Yes, I can use this, you betcha. But in using this, you have to be careful. That's revealed to us by answering correctly the second question. Is this equilibrium stoichiometric? Why not? Have we not realized, at least it was part of our conversation, that carbonate ion and deionized water hydrolyzes 70%. That means 30% of it's still there. You see any carbonate ion in this equilibrium reaction? You see calcium carbonate, but you don't see any carbonate ion. Yet it's there, isn't it? This equilibrium reaction doesn't show that. What does that tell us for this system about the molarity of calcium ion compared to the molarity of hydrogen carbonate ion? Which has the greater, higher molarity? Calcium ion, it has to. Now then, here's the K expression. To evaluate this K expression, I go back to the equilibrium reaction. Here it is. And I let this thing talk to me. I want to know, what are the fundamental equilibrium constants of which this reaction is composed? Because I need to know the answer to this in order to evaluate K for this equilibrium reaction. Because K for this equilibrium reaction is not given. Of course, it's in the notes. But it's not an equilibrium reaction for which the K value will be look-upable in any book, unless I write the book. How do I let this equilibrium reaction talk to me to tell me what K's I'm looking for? Do I see a semi-soluble salt? That guarantees that one of the component K's of this equilibrium reaction is KSP for this stuff. Will it be KSP or 1 over KSP? It'll be KSP. Remember how KSP is defined? Salt on the left, double arrows, component ions on the right. Now, if I had the salt on the right as a product, then it'd be 1 over KSP. Okay? What else is this reaction showing me? At least implicitly. Because the carbonate ion component of calcium carbonate is not a product. So something's got to be happening to the carbonate component of this stuff as this reaction proceeds left to right. What is it that's happening to this? It's hydrolyzing, isn't it? It's reacting with water to convert to this stuff and this stuff. So what's the other K value that I'm looking for? KB carbonate. Yeah, you let this damn thing talk to you and you'll know what K's to look for. And indeed, by taking the equilibrium constant for this reaction and multiplying by carbonate molarity over carbonate molarity, I see what we just concluded. KSP calcium carbonate is the molarity of this times the molarity of this, and KB carbonate is the molarity of this divided by the molarity of this. So I'll put it in numbers and I evaluate K for this. I get 1.3 times 10 to the minus 12. Now, let's put this value to use to get at the solubility computation. Here again is the equilibrium constant expression. Oop. It's equal to 1.3 times 10 to the minus 12. And we've already recognized that the solubility of the salt calcium carbonate will be equal to the concentration of what system component? The solubility of calcium carbonate in this system will be equal to the molarity of what system component? Calcium ion. Right? The hydroxide ion molarity is fixed, is it not? System's buffered at pH 8.00. Hydroxide ion molarity is 1.0 times 10 to the minus 6. So as things presently stand, we have one equation and two unknowns. Because we know that carbonate ion in this system has converted to hydrogen carbonate ion, but in order to know how the molarity, equilibrium molarity of hydrogen carbonate ion compares to S, we got to know to what extent the carbonate ion reacted. Now, do you remember the extent to which carbonate ion reacted when we saturated straight water with calcium carbonate? 70%. Will the carbonate ion react to a larger extent or smaller extent in this system? Which is a question we've already answered. Larger, because the system is more acidic. Yeah, how about that? But now let's get a quantitative relationship involving the molarity, equilibrium molarity of hydrogen carbonate ion to S, while also realizing this. This we know, and we also know that the molarity of this, which is S, is equal to the sum of these terms. Is that correct? Go back to that equilibrium I, the dissociation equilibrium for calcium carbonate. You see it up there? That puts carbonate in the system. If the carbonate sits there and doesn't do anything, then the carbonate ion molarity is also equal to S. But if the carbonate ion hydrolyzes, which we know it does, then at the minimum, carbonate ion converts to bicarb ion. And if you make the system progressively more acidic, to what will bicarb ion convert? Hydrated CO2, quote unquote H2CO3. So if I sum the molarities for all possible forms of carbonate ion, material balance for carbonate ion in this system, I get this, and that's got to equal to S, which is the same as calcium ion molarity. All right? Now then, just for fun, we're going to prove this in a moment, but just for fun at this stage of the game, we got the system buffered at pH 8. Which molarity? This and or this, do you think can be struck from this relationship at pH 8? You're betting H2CO3. And that is because H2CO3 is acidic. But this system is mildly basic, is it not? Now, do you think it's possible at pH 8 we might also be able to strike the carbonate ion molarity from this relationship? Remember what we know. At pH 10, to what extent did carbonate ion convert to hydrogen carbonate ion? 70%. And this is pH 8. It's 100 times more acidic. So at the minimum, we know the carbonate ion is going to convert to bicarb ion a hell of a lot more effectively. You agree with that? Let's find out just how effectively. What do we do to answer that question? We can use KB carbonate. We can use KaH2CO3. But I'm going to use, there's nothing wrong with using what we just said. Ka this and Kb this. Because what we are needing to do, let me tell you this before we do it, is to establish a relationship between the relative molarities of this to this as a function of pH and this to this as a function of pH. Ka bicarb allows us to get the relationship between this and this as a function of pH, and Kb bicarb allows us to get the relationship of the molarity of this to this as a function of pH. You know this? There again is Ka bicarb, where bicarb reacted water protonate water and make hydronium ion. And here, bicarb is behaving as a base and extracting H plus from water. To make the conjugate acid of bicarb, which is hydrated CO2, and hydroxide. So let's write Ka and Kb this I remember, but we've used this value before. You know how to get it. And now we are in position to answer the question. How do the molarities compare for the various forms of carbonate-containing stuff? Because by answering this question, we will know how the molarity of bicarb in this system compares to S. All right? Oops, I ought to finish this. 10 points off. I didn't finish the concentration term. Now what I'm going to do is to rearrange this so that I have a concentration ratio of bicarb to carbonate. I want the bicarb on top because I already know at a glance that the bicarb molarity is bigger than the carbonate molarity. In fact, without even glancing at this, I know the bicarb molarity is bigger than the carbonate molarity, right? Then it hydrolyzed 70% in straight water, is hydrolyzing to a larger extent here. Whatever the bicarb molarity is, it's got to be bigger than the carbonate molarity. So I'll write this. Do you accept this? Or are you mystified by this? And you're saying, where the hell did he get that? Isn't the system buffered at pH 8? That means hydronium ion molarity of 2 sig figs is 1.0 times 10 to the minus 8. All I did was to take this relationship and rewrite it so that I got bicarb molarity up here, carbonate molarity down here, hydronium ion molarity stays where it's at, and Ka goes down there. That's what I did. So I got 1,000 divided by 4.8. What's that gimme? I got the results here, 200 and something. 210 to 1. Do you accept my statement now that practically speaking there's no carbonate in the system? Because the molarity of bicarb is 210 times greater than the carbonate molarity. Now let's look at bicarb and H2CO3. Play the same arithmetic game that I played here. I want a ratio of this stuff divided by this stuff. So this goes here, and this goes underneath hydroxide ion molarity. I put in the numbers. And what do I get for this thing? 42 to 1. Now do you accept my statement that the only carbonate form that means anything in this system is HCO3 minus? Fair enough? So let's go back to the relationship we have at the top of the board. And recognize that what we have established is that question mark, which we used previously to represent the equilibrium molarity of bicarb, compares how to S? Same as S, isn't it? For this system. I mean, because what we did was to look at this and say, this doesn't matter and this doesn't matter. Right? Oh, there it is. So here comes the tough part. 1.3 times 10 to the minus 12 equals S squared times 1.0 times 10 to the minus 6. Tough phooey. Calculate S. And here we go. 1.1 times 10 to the minus 3, which is a bigger number than this number, and which we knew that had to be a bigger number than this number, because at pH 8 the stuff's got to be more soluble. It's about 1.1 times 10 to the minus 3 versus 1.4 times 10 to the minus about 8 times more soluble. All right? Now then, look at what's on the board and recognize that a couple of questions further into the notes will say S CaCO3 in pH 6.00. buffered solution? I ask this question now because the considerations that we must make are presently on the board. For starters, at pH 6.00 buffered solution, or in this solution, how will the molarity of calcium carbonate compare to 1.1 times 10 to the minus 3? Same as, bigger or smaller? I'm not hearing many responses. It's got to be bigger, damn it! Isn't this system 100 times more acidic yet? So we're killing carbonate ion now all the more effectively. What happens to the bicarb carbonate ion ratio when I change the pH from 8 to 6? What's this ratio going to be? At pH 6. There's the ratio at pH 8, 210 to 1. What's this ratio at pH 6? I'm listening. Let these numbers talk to you. 21,000 to 1. So if you thought you could forget carbonate at pH 8, you sure as hell can forget carbonate at pH 6. Now then, what happens to the bicarb hydrated CO2 molar concentration ratio at pH 6? What does this become? This becomes 0.42 to 1. Aha! So at pH 6, what is the predominant form of carbonate ion in this system? What is it? It's hydrated CO2, isn't it? But at pH 6, is hydrated CO2 the only form of carbonate we have to pay attention to? No, because bicarb is still a species whose concentration must be reckoned. Right? Good. Now then, let's at least lay foundation for the next consideration, which is salt effect. This is not a chemical effect. This is an electric effect, a Coulombic effect. There's the equilibrium established. The equilibrium established by saturating deionized water with silver chloride. Equilibrium between silver chloride, silver ion, and chloride ion. And we have recognized S silver chloride equals square root of KSP. Because neither silver ion nor chloride ion have any acid-base properties of consequence in water solution. So, from an analytical standpoint, that calculation is simple. Now comes the fun part, the part which illustrates the salt effect. How about S AgCl in, say, 1.0 molar sodium nitrate solution? Now, what we're asking is, does the presence of sodium ion at high concentration, as well as nitrate ion at high concentration, have any impact on the solubility of silver chloride in water? First of all, does sodium ion in water solution react with silver ion or chloride ion? No. Does nitrate ion in water solution react with silver ion or chloride ion? No. Case again is, point again is, this is not a chemical effect. It's an electric effect. Now let's go to the laboratory, or imagine such, and make the measurement. And what do we find out? That silver chloride saturated in 1.0 molar sodium nitrate solution shows a solubility which is A, the same as it is in deionized water, B, smaller than in deionized water, C, greater than deionized water. And the answer is greater. The question is why. We'll pick it up from this point next time.